Okay, this is session 8, week 7. And the first thing we're going to do is go through quiz 5 solutions. Just like last week, you guys did great. I didn't see many problems here. So we'll just briefly go through the work. The first problem was asking us to give a sketch of level curves. Okay, so we have a square root of this expression, 2 minus x squared minus y squared. So notice the domain of this function is all values or all points inside this circle of radius 2, which means that those are the values for z that we should be picking, and that's important. We can't just pick any number because we might end up having an expression that says x squared plus y squared equal to negative number, which is impossible, right? So it's helpful sometimes to look at the domain of our function first and then say, okay, so I have to pick values in this range right here. So you see that I constructed a table and I picked 5 level curves, looks like, and they are circles, right? So they're circles with these radii that are not really nice numbers, but that's okay. So we just look for the idea of how this surface is built. Okay, so that's problem 1. No problems here. Problem number 2, I asked to compute a limit. Okay, a couple of different ways to solve this problem. If you plug in your point for 1, you see that we have this expression in determinant form, 0 over 0. So some students multiplied by the conjugate expression and then simplified. I factored the top. Okay, I factored it completely, so I have y as one of my factors, and then square root of x minus 2 square root of y, which cancels out with the bottom. So that's nice because now we can evaluate this expression, gives us a nice limit, so we have a removable discontinuity at that point for 1. What does that mean? In the graph, there's just a hole at that particular point. And then the last problem was pretty good. So here I ask you to determine the domain of this function. So a couple of things we need to worry about, division by 0, and then the expression under the radical being positive. So we set up our inequality. It turns out to be x squared plus y squared greater than 9. So it's all the points that are outside of the circle centered at the origin radius 3. Okay, so students did good with that one as well. All right, so these are the 3 problems, and like I said, the class did really well with this one. Okay, are there any questions? Is this okay now? Okay, so then if we're done with this, let me go ahead and share. What am I going to share? I'm going to share the notes for today's lecture. And if you looked at the notes already, you see that there's a lot of stuff to cover. So I might go just a little bit um, faster than typically, only because I want to make sure we cover everything. Okay, so last week we talked about computing partial derivatives, right? So one way to think about a partial derivative is how your function is changing in just one direction. So if you say, okay, I want to see what the rate of change is in the x direction, that means we keep y fixed and we compute the derivative with respect to x, and it tells us how my function is changing only if I'm moving in the x direction and y is fixed. Hence, we set up our derivative by treating the y variable as a constant. Okay. Similarly, we can think about the partial derivative with respect to y as the rate of change of my function as we're moving in the y direction only. Okay. So that's your interpretation of partial derivatives, and not. But now we're going to consider the chain rule. Okay, what if we have more than just 2 variables involved? So what's the deal here? Let's say we have a function. This is your general notation, some function of x and y, and each function, x and y, are also a function of another variable. So let's say x is a function of t, and then y is also another function of t. Okay, so we have function composition, and I would like to compute the derivative of z with respect to t. How would I do this? So here's your general rule. If it's a function of two variables, what do we do? It's partial of z with respect to x times the derivative of z with respect to t, okay, plus partial of z with respect to y times derivative of y. Oops, sorry, this should be over here. This should be x, not z. This is y with respect to t. Okay, and let me highlight these. These should match. Partial of z, and then this is derivative of z, and then partial of y, this is derivative of y. And this, of course, can be extended into more variables. So maybe you have three variables, function of x, y, and z. Okay, and then each function x, y, and z also depends on two other variables. So this could be extended infinitely many variables. So we're going to go ahead and take a look at this simple example first, and then we'll get into more complicated problems. The first problem says the following. I have my function here, a polynomial function, in terms of x and y, and x is also a function of t, it's sine of 2t. Y is also a function of t, which is cosine of t. So we want to evaluate dz dt at t is equal to 0. Okay, so how do we do this? All right, so let's go ahead and talk about the notation. So this would be dz dt evaluated at t is equal to 0. Okay, so I'm going to set up my general formula. So that would be partial of z with respect to x times dx dt plus partial of z with respect to y times dy dt. Okay, and then evaluate all of this at 0. Now we can evaluate x and y at 0 already. So x evaluated at 0, that's sine of 0, that's 0. And then y evaluated at 0, that's going to be cosine of 0, which is 1. Okay, so now let's see how we do this computation. Dz dx, partial of z with respect to x. Okay, so that would be 2xy plus 3y to the fourth. Okay, times dx dt. Okay, derivative of sine of 2t, that would be 2 cosine 2t. Okay, plus dz dy, partial of z with respect to y. Okay, what is this? That would be x squared plus 12xy cubed. And derivative of cosine, that would be negative sine of t. And then we're going to evaluate this at 0 eventually. Okay, well, we can do it now. So everything is written in terms of our derivative. Now we just need to evaluate it. So what's going to happen here? This is going to be 2 times 0 times 1 plus 3 times 1 to the fourth. 2 cosine of 2, 0. So that's 2 cosine of 0, right? Okay, plus 0 squared plus 12 times 0 times 1 cubed. So this expression will be 0. Okay, this whole thing is 0. And what do we get here? Here we get a number that's not 0. Okay, so we get 0 plus 3 times 2 cosine of 0, that's 1 times 2, so the final answer is 6. Okay, so take a look at this solution. Okay, see what we've done here. We just followed this formula carefully and then evaluated the final expression at t is equal to 0. Okay, I'm going to give you a minute to take a look at this. Let me know if there's any discussion. No questions? Is this all good? All right. Okay, then let's take a look at the next problem. Okay, so here we have a function of two variables, x and y, and then x and y are also functions of three variables. We have u, v, and w. So there is all sorts of function composition here. And we would like to compute these three partial derivatives with respect to u, v, and w, and also evaluate it. Okay, so we want to evaluate all of these derivatives at these values of our variables. Okay, so that's the goal. So let's go ahead and do the computation. Here we're looking for three partial derivatives evaluated, which means the answer should be three numbers. Okay, all right, so let's see. Let's go ahead and set up our first derivative. So this would be f with respect to u. Okay, what is the setup here? It's going to be df dx times, now we have partial because x is a function of three variables. So partial of x with respect to u, okay, plus df dy times partial of y with respect to u. Okay, so let's compute this expression here. Df dx, what is that? That would be 2x plus 3y. Nope, not 3y. Y cube, right? Okay, and then dx du. Now I need to differentiate this expression right here with respect to u. So what do we get? We get v squared, right? Because the partial with respect to u of w cubed, that's just 0. Okay, plus df dy. Df dy. All right, what is that? That will be 3xy squared. Okay, and now we need to differentiate this expression with respect to u. Okay, that's just going to be 1. Okay, so that's our setup here. So what are we missing? We need to find the values of x and y with these values of u, v, and w. So I'm going to evaluate my x here. Okay, that's going to be 2 times 1 squared plus 0 cubed. So that's just 2. And then y is going to be 2 plus 1 times e to the 0. So that looks like it's 3. Okay, so now we can evaluate it. Okay, so f of u evaluated at those values. Okay, at 2, 1, 0. And now we just plug in our numbers here. So 2x plus y cube. Okay, what is this? That would be 2 times 2 plus 3 cube And what do we get for v squared? V squared, that's just 1 squared. Okay. And then here we get 3 times 2 times 3 squared. And this is still 1. Okay. So you can do this quick computation. The answer should be 85. Okay. So partial derivative with respect to u of this function is 85. What does that mean? Now this is difficult to visualize because you have a function of 2 variables, right? And you also have this composition where we have each of x and y is also a function of the other 3 variables. Okay, but one way to think about it, this is rate of change in the direction of u. Okay, when everything else is fixed, if we're just moving in the direction of variable u, that's what we get. Okay, so that's our first partial derivative. Let's go ahead and compute the other two. So that part is done. Let's go ahead and compute f of v. Similar setup. df dx times dx now with respect to v plus df dy times dy dv. So notice that we're going to have the same expression over here and over here. Okay, so we don't really need to worry about computing it. We know what they are, right? So that would be 2x plus y cubed here and 3xy squared here. Now we just need to compute the partials. So the partial of x with respect to v, okay, what is it? That's going to be 2uv. Partial of y with respect to v, what is that? That would be e to the w. Okay, and now these numbers right here, the ones that I'm going to highlight, we already know what they are. Okay, so we've computed them in the previous problem. So this turns out to be 31, and this value right here is 54. So now we just need to evaluate the missing parts, right? So f v is equal to what? This is 31 times 2 times 2 and times 1 plus 54 times e to the 0, which is 1. Okay, so we get 178. That's going to be the answer if you compute this carefully. Okay, so that's our second partial, and now we have one more to cover, okay, to compute. Partial with respect to w. Let's do the general setup. df dx times dx now dw plus df dy times dy dw. Okay, notice again these expressions are the same as we've already computed, so that saves us some time. Okay, I'm just going to write the number here, so that's going to be 31 times what? Partial of x with respect to w. That's going to be 3w squared, okay, plus 54 times what? Partial of y with respect to w. That's going to be v e to w. Okay, we can compute this. So this is 31 times 3. W is 0, so this expression is gone. And here we get 54 times 1. So the final answer is 54. Okay. All right. So let me project this solution. Okay. Take a look at this. See if there are any questions, anything you would like to discuss. Okay, all right. So let's take a quick look what we've done here. Our chain rule that's expanded, right, to function of multiple variables. Okay, and you can see that you could have x, y, and z, right? So if you have x, y, and z, then you just have one more component there. You add one more thing, right? So what do I mean by that? Let me go ahead and add a page, and you'll see what I mean. Oop, how do I add a page? Oh, let's add a page. Okay. Yeah, let's take a look at this quick general example. Let's say I have a function of x, y, and z, right? Okay. And x is also a function of, let's say, two variables, t and s. And y is a function of two variables, t and s. And z is also a function, what I want to call it, let's say k of t and s, okay? Then we can compute two partials here, right? So let's say we compute partial of f with respect to t. What would that look like? That would be partial of f with respect to x times dx dt, okay, plus partial of f with respect to y times dy dt. And then we get one more here, partial of f with respect to z times dz dt. Okay, so let me show you how some of my components match up, right? So I have these parts are matching as far as the variable goes. And notice I have everywhere I have my derivative with respect to t. So this is going to be how we compute partial if we have a function of three variables. Now you can see how this can be extended to any number of variables, right? Now what about the other variable? Yes, the same idea, df ds. Okay, still compute the partial of x first, oh, partial of f with respect to x, and then we just repeat this. Okay, now I'm going to have s as my variable of differentiation here everywhere, dy, ds, and then the last component will be df dz times dz ds. Okay, so just like before, look what happens here. I want to make sure these match up. Okay, this is no different than our chain rule from calculus 1, except over there we only had one variable, right? Okay, and then you have s as your variable of differentiation. All right, so a good practice would be, just pick out your own function, whatever you want to come up with, and say what if I assign my variables x, y, and z to be functions composition of other variables, okay, and see if you can compute partial derivatives. All right. So that's your general setup for computing partials of functions of more than just one variable. Okay, now let's talk about the directional derivative and the gradient. So what is happening over here for this particular chapter? Let me give you a little bit of a conceptual understanding. What is it that we're doing here? So we're working with objects in 3 space. So here's your 3 space, R3, that's where we live. Okay, let me label my x's. All right, and imagine we have a surface. So we're working with a surface that lives in 3 space. Okay, so something like this. Okay, and we have a point on this surface with some coordinates. Okay, so when we computed our partial derivatives with respect to x and with respect to y, what is it that we've computed? Okay, so let's say we've computed dz dx. Okay, and let's say we have a function. So we have an equation that describes this surface right here. When we compute dz dx, what is it that we're computing? We're finding rate of change at a point if we just move in the x direction. So if I sit at that point and I start moving in the x direction only, that's what my partial derivative is telling me if I evaluate it at that value of that point, right? So it is rate of change in the direction of x. Okay, so let me write that out. Rate of change in the direction of x. Okay, similarly, dz dy would be rate of change in the direction of y. Okay, so two directions, right? But you say, wait a minute, but we can go in many directions. What if I don't want to go in just x direction? I want to go, let's say, in the direction of this vector right here, or maybe this way. There's infinitely many ways that I can go through starting at that point on the surface. What if I want to go in that direction? Okay, how do I determine rate of change if I don't just follow along x or y axis? Okay, that's what the directional derivative is going to tell us. Okay, so the directional derivative tells us the rate of change in the direction that you would like. Okay, and it's very easy to compute. So here's your general formula. We need a unit vector. Okay, and this is important. It has to be a unit vector in the desired direction. And that's one of the reasons why we discuss how we compute the unit vectors to begin with, right? Okay, and then we need to compute the gradient vector. Okay, the gradient vector just consists of partial derivatives of your function here. And once we compute those two, we take the dot product of these two vectors. So here's your notation, capital D, subscript u. Okay, this means directional derivative of my function. Okay, in the direction of my vector u. Okay, that's what this notation means. And notice that this is a dot product. We're going to get a number, right? A dot product of two vectors gives us a number. Okay, so let's go ahead and consider the first example, and you'll see how to find these directional derivative. And in general, students have very little trouble with this. Okay, so first problem says compute the directional derivative at point 41 in the direction. So let me highlight some elements here. 41 in the direction of vector v, negative 1, 2. And here's my function, right? So my function is x over x minus y. Okay, the first thing I'm going to decide if this vector is a unit vector. So I'm going in the direction of vector v, but that's not a unit vector, right? You can clearly see it. Okay, the magnitude of this vector is root 5, definitely not unit. Okay, so now I'm going to come up with the unit vector. The unit vector that we're going to use is negative 1 over square root of 5, 2 over square root of 5. Okay, that is a unit vector in the same direction. Okay, same direction as my vector v. Okay, so unit vector is computed. We're good to go. Now, second part is computing the gradient vector. Okay, so that means I need to find partial derivatives of my function. Okay, so partial of f with respect to x. Okay, What is it? I need to use chain rule here. I'm sorry, not chain rule. I need to use quotient rule, right? So this is x prime times x minus y minus x times x minus y prime over x minus y squared. And I keep in mind that my prime is done in terms of x with respect to x. Okay, so we get x minus y minus x over x minus y squared. So the final answer for this partial is negative y over x minus y squared. Okay, that's my partial derivative of this function with respect to x. Second part is partial with respect to y. Okay, basically the same setup, except now I'm differentiating with respect to y. So x prime with respect to y, that's 0. So that term is gone. So I'm going to have negative x times negative 1 over x minus y squared. That gives us x over x minus y squared. Okay, so that's going to be your gradient. So let me give you a general notation for gradient of this function. This is upside down triangle. Okay, gradient of f is a vector with these components. First component is negative y over x minus y squared. Second component is positive x over x minus y squared. Okay, gradient is a vector. Okay, so we've computed the actual gradient. Now we can evaluate it at that point. Okay, so gradient of f evaluated at the point 1, 4. I'm sorry, 4, 1, the other way around. Okay, so now I'm just plugging in my numbers for x and y. What is that going to be? So it's going to be negative 1 over what? X minus y squared. That's 4 minus 1. That's 3 squared, so that would be 9. And then here we get 4 over 9. Okay, so that's the gradient of my function evaluated at that point. So one last step. Now we compare V. What is it? It's the dot product, okay, of my unit vector. So my unit vector is negative 1 over root 5. First component, second component is 2 over root 5 dot this vector right here, negative 1 over 9, 4 over 9. Okay, and I'm going to let you do the arithmetics here, but we're going to get 1 over root 5. That's going to be the value. So we get a number. Okay, what does that tell us? This is the rate of change. If I'm standing at that point on the surface, point 41, and I'm going to start moving in the direction of this vector v, then the rate of change is 1 over root 5. It's positive, right? Okay, this is a positive change, so looks like I'm going to be going up on the surface. Okay, so that's your first problem for computing the directional derivative. Okay, I'm going to give you a moment to absorb this. Okay, go over the solution. Let me know if you have any questions. No questions? Okay, then let's keep going. Okay, let's do one more problem. compute the directional derivative at the point -1, -1. We have direction v of the vector with components 5, -2. And here I have a function of two variables, sine of pi 2x minus pi y. Okay, let's see what we got to do here. So first things first, this vector is obviously not a unit vector. Okay, so the magnitude of vector v is 5 squared plus -12 squared, square root of this. You see that these are Pythagorean triples, right? It's going to be square root of 169, so that's 13. Okay, so from here, I know the unit vector that I'm going to be working with is going to be 5 over 13, -12 over 13. Okay, that is a unit vector. Now I'm going to compute my gradient. Okay, the gradient of this function, partial with respect to x. Okay, partial with respect to x. Derivative of sine is cosine, so I'm going to get cosine of the same argument times the derivative of the inside with respect to x, that's going to be 2 pi. Okay, similarly, partial with respect to y, derivative of sine is still cosine, so that argument stays the same. And now partial of the argument with respect to y, in this case, that's negative pi. Okay, so that's my general formula for the gradient. Now let's evaluate this at p. Okay, so -1, -1. Those are the numbers I'm going to be plugging in. So 2 pi cosine of what? That would be -2 pi plus pi, right? So that's going to be -pi. And then here, this is -pi cosine of also -pi. Okay, let's see what we get. Cosine of -pi. What is that? It's -1, right? Okay, so cosine of -pi, that's -1, so we get -2 pi here. And then for the second component, we get positive pi. All right, so that's our gradient evaluated at the point P. Now we can compute the directional derivative in the direction of vector v. Okay, what is it? It's the dot product of the unit vector in that direction with the gradient evaluated at that point, 2 pi, pi. Let's see what we get. So we get -10 pi over 13 minus 12 pi over 13. Okay, so what is this? That's going to be -22 pi over 13. Okay, that's our final answer. How would you guys interpret this value? What can you say overall about the surface, about, what's happening? What does that number tell you? Think about it for a moment. Any ideas? What does this number tell you? So in a full sentence, just like I've discussed it for the previous problem, what's happening here? it's always a good idea to take that math, right, and put it in simple words. So I have this number, but what does it mean? How would you explain it to, let's say, like 11th grader, right? So they know a little bit of math. They might not know about derivatives, but so what? So we computed this number. What does it tell you?
Is the plane kind of dipping downwards at that point?
Yeah, you're in the right direction. So what I'm looking for is something like this. Let's say you are standing at that point. Remember, this is all in reference at that point because that's important. Our values will change if we plug in different values, right? So if we're standing at that point, -1, -1, right? You're standing on the surface and you start going in the direction of vector v. This is how fast you're going down, right? So negative, okay, tells you yes. So that you can say that this the surface is sloping down, okay, and it also tells you how fast it's going down. So this is kind of giving you the rate of change in a in a higher dimensional space. Okay, but which direction are we going? Not just any direction. We have to be going in the direction of that vector v. Okay. So yes, we have decreases or downward slope, sloping down. But again, the important part here is it's at that point. Okay, if we plug in a different point, then the situation might be different, right? Okay, good. So that's the it's a good way to really connect these computations to what does it really mean? Like why do we bother? Why do we care about these kind of stuff, right? Okay. All right. So what do you guys think of computing directional derivative? Any questions here? Are all the steps clear? Okay, if everything is good, okay, let's go ahead and take a look at the following theorem that we're going to discuss. The theorem says the following. If we have function f that's differentiable at a point and the gradient is not 0 at that point, okay, then we can talk about maximum rate of increase and maximum rate of decrease. So this is your big interpretation of what a gradient is telling you, okay? So one way to think about it, this theorem is like properties of gradients. What does it actually tell you? Okay, so the first thing that we need to remember that f has its maximum rate of increase in the direction of the gradient. Okay, that's the big deal about the gradient. Okay, so let's say you're standing at a point um, at the at the bottom of a mountain, right? And you want to know in which direction you need to go so that you have the maximum rate of increase, the steepest, right? The steepest direction of what is it? That's going to be ascent, right? Okay, so maximum rate of increase. That means you need to be going in the direction of the gradient, whatever that gradient is. So compute the gradient of your function. That's the direction you're going to. Okay, and then the rate of change is just the magnitude of the gradient evaluated at that point. Okay, similarly, f has its maximum rate of decrease, okay, in the direction of negative gradient, okay. So again, if I were to descend, okay, and I want to know what is the direction that I gotta go so I have the steepest descent, okay, the direction is the gradient, and the rate of change is just the magnitude here, okay. Now what if I want to travel on my surface and I don't want to have decrease or increase or decrease, right? Okay, so the directional derivative is 0, okay, meaning there is no change. there is no change on the surface, okay, in any direction that's orthogonal to your gradient. Okay, so these are the three properties of the gradient that we should be aware of. Okay, so let's go ahead and take a look at a problem here. Okay, the first problem gives us this function of two variables. We have a point, okay, and we're going to answer all of these questions, find a unit vector that gives the direction of the steepest ascent, steepest descent, and then also vector that points in the direction of no change. Let me give you a pictorial representation of no change. Okay, let's say we have a sphere, right? Okay, so I have a sphere, and let's say I have a point on the sphere right here. Okay, so if I go, let's say, in the direction of this vector, looks like I will be increasing, right? So we will be increasing on the surface going up. And if I go in the direction of this vector, then we'll be going down the surface. So the directional derivative will be 0. But what if I just go along this circle right here, right? Then there's no change. I'm just walking on this sphere and there's no vertical change at all, right? Okay, so that's what that means, the direction where there's no change. Okay, so let's go ahead and compute these values. Okay, find a unit vector that gives us the direction of the steepest ascent and steepest descent. This is another way of saying find the gradient, evaluate it at the point, and then if it's not a unit vector, make it a unit vector. Okay, so we know how to compute the gradient. All right, we need to compute our partial derivatives. Let's do it carefully. Partial with respect to x. Okay, I'm going to rewrite this function like this: 20 plus x squared plus 2xy minus y squared to the power of 1/2. Okay, then to compute my partial with respect to x, okay, this is going to be 1/2 times this expression here to the power negative 1/2, right? Times the derivative of the inside with respect to x, which is going to be 2x plus 2y. Okay, I'm going to simplify this. We can reduce this common factor of 2. So I'm going to get x plus y on top. On the bottom, I'm going to get square root of this expression. Okay, now this step is crucial, right? We need to compute this very carefully because that's the first step, and then everything else depends on it. So please be careful when you compute these partial derivatives. Try not to make mistakes that will lead to incorrect answers. Okay, similarly, let's go ahead and compute partial with respect to y. Same idea. We're going to apply power rule first. Okay, times the derivative of the inside with respect to y. What is it? And that's going to be 2x minus 2y. Okay, so that gives us x minus y. Denominator is the same. So that's my gradient for this function in general form, right? So as a function of x and y. Okay, and now we can evaluate this gradient at which point? Let me see, where's the point? Right here, 0.12. Okay, so gradient of f evaluated at 1, 2. What is that going to be? Okay, 1 plus 2, so that's 3. Let's compute the numerators first. 1 minus 2, that's negative 1. Okay, and now we do what? So we do 20 plus 1 squared plus 2 times 1 times 2 minus 2 squared. You can compute this. It's not going to be a perfect square, it's just going to be square root of 21, which is fine. Square root of 21. Okay, so that's our gradient evaluated at that point 1, 2. Okay, let's go back to the theorem. What does it say? F has its maximum rate of increase at AB in the direction of the gradient, right? So if I go in the direction of the gradient of this vector here, then that's going to be my maximum rate of change. Okay, but that's not what this problem is asking. It's asking find the unit vector or a unit vector that gives you the direction of steepest ascent. Okay, that's just another way of saying which way we're going to go so that the rate of change is highest. This is the direction. However, this is not a unit vector. Okay, we can make it a unit vector. We need to find the magnitude. Okay, the magnitude of f of gradient evaluated at p. What is it? Okay, so that's going to be 9 plus 1, that's 10 over 21, square root of this. Clearly, this is not 1, so that's not a unit vector. Okay, so to find a unit vector, we need to take our gradient and then divide it by this value here. Okay, so that's 3 over root 21, negative 1 over root 21, divide by root 10 over root 21. Okay, and that turns out to be what? So this is going to be 3 over root 10 minus 1 over root 10. This is a unit vector. Okay, you can check. If you compute the magnitude of this vector, it's going to be 1. So this is a unit vector. Okay, so let me write it out over here. Okay, U subscript A. I'm going to use that for ascent. Okay, with components 3 root 10, negative 1 over root 10. That's the unit vector in the direction of steepest ascent. Okay. Now, what about unit vector in the direction of steepest descent? Not much work to do here. We already done most of it. Okay, so let's say U subscript D. That D stands for descent. It's just the opposite. We're going to go the opposite way. So negative 3 over root 10, positive 1 over root 10. That's going to be unit vector in the direction of steepest descent. Okay, so we found 2 unit vectors. If we go in direction of 1, that's going to be the hardest, right? It's going to be going up. So that's the tough one, okay? And then going down, okay, also pretty fast, right? The steepest descent, okay? So the highest rate of change, except that now you're descending, okay? What else do we need? Let's take a look. Find a vector that points in the direction of no change. Find a vector where if we go in the direction of that vector, we're not changing at all for on the surface, right? Let's go ahead and see what that theorem says. It says the directional derivative is 0 in any direction that's orthogonal to the gradient. Okay, orthogonal to the gradient. Okay, now this one doesn't say unit vector, so you can still find a unit vector if you'd like. But let's think about it. I want to find a vector that's orthogonal to the gradient. How would I do that? I'm going to let you think about it and see if you can answer that question. How do we find vectors that are orthogonal to something? You guys know it. So that's why I'm not just telling you, because you know how to do it. Okay, so find vector which dot product with vector ud is equal to 0. Yes. Okay. Now some of you might be tempted to use a cross product, right? But we can't do cross product here. We have vectors with two components. But dot product, yes, dot product is 0. And that can be many, many different vectors. But what's one of them? Okay, so what would be one vector so that I take that vector and I dot it with the gradient and I get 0?
Can we treat point P as a vector to get it orthogonal to both of those?
Okay, repeat that question, please.
Could we dot product the point P and the gradient, just treat the point P as a vector for this problem?
So if you dot 1, 2 with the gradient, I don't think you're gonna get 0, right? I mean, you can check.
Oh, right. I was thinking you needed 2 for the cross product. I was thinking of the other thing.
Yeah,
Never
yeah.
mind.
So we're not gonna do cross product, right? So we can't do cross product. Cross product is defined for vectors with three components, right? Okay. So I see Sergey says 1 over root 10 minus 3 over root 10. Does that work? It almost works, but not quite. Yep, we gotta have both pluses, right? So 1 over root 10, 3 over root 10. That should work. Okay, you can check. So if you dot that with u of a, that you're gonna get 0, right? Okay. So, but there's many, many ways to do it. Okay, you can just pick one component, and then that will determine uniquely what the other component is. Okay, so that's one vector, so that if you go in the direction of this vector, there's no change. Okay, so that works. You can check the dot product of, so you can check this, u subscript a dot v is going to be 0. Okay, so here's your problem where we have all sorts of concepts kind of mashed together, right? So we have partial derivatives, we have gradient, we have unit vectors and directional derivative, and the properties of the gradient. So this is a good problem that I often put this kind of problem on an exam. Okay. So one of the most crucial parts of the solution here is computing that derivative correctly. Okay, the partial derivatives. All right, you guys have any questions? Take a moment of take a look at the solutions. Let me know if we need to discuss anything. Okay, if there are no questions, then we'll do one more problem. And then the third problem, I'm gonna let you try on your own and see if you can, sometime after the lecture, you can figure out the solution to problem number 3, the one that says try this. Okay, we'll do problem 2 together. Same idea. We want to find those three vectors. Okay, so this is just another computational practice problem. Let's find the gradient here. The gradient is going to be the vector. Derivative of sine is cosine. And then the inside with respect to x is 2. So, well, let me think about it for a second. Is that right? 2 cosine. Yeah, that's fine. Okay. And then here we get, oh, wait, there's another 2. So 2 times 2, that's 4. Here we go. Okay. The other partial derivative is going to be cosine of 2x minus 3y. And then 2 times negative 3, that's negative 6. Okay, that's my gradient as a function of xy. Now we can evaluate this at the point 0, pi. Okay, what's going to happen? This is 4 cosine 2 times 0 minus 3 pi, so that's going to be negative 3 pi. And then here we get negative 6 cosine, same idea, right? So also negative 3 pi. Okay, cosine of negative 3 pi, that's going to be negative 1, right? So we get negative 4, positive 6. That's the gradient at that point that we're interested in. Okay, what is the magnitude of this vector? Okay, the magnitude, that's negative 4 squared plus 6 squared. So 16 plus 36. And once you simplify it, it's going to be 2 root 13. Okay, obviously this is not a unit vector. So the unit vector in the direction of the steepest ascent, okay, what is that? That's going to be negative 4 over 2 root 13, positive 6 over 2 root 13. We can reduce this vector, so we get negative 2 over root 13, 3 over root 13. Okay, you can check that this is indeed a unit vector, right? We're going to get 4 plus 9, that's 13, divide by 13, that's 1, so that's your magnitude. So it's always a good idea to check if what you get is actually a unit vector. Okay, so the second part is easy. Once you compute that vector in the direction of the steepest ascent, steepest descent is just the opposite. So that would be 2 over root 13 negative 3 over root 13, also a unit vector. Okay, and now the last part, I would like to find a vector in the direction of no change. Okay, so I want to find, actually let's go ahead and find two vectors in the direction of no change. So v1, okay, so no change. Let's go ahead and make that note here. No change. v1. Can somebody give me a vector so that if I go in the direction of that vector, there's no change? Okay, I'll give you one. How about this one? 6, 4. That should work. Okay, so 6, 4, if I do this, I'm going to get negative 12 on top. for the first component, and then I get also positive 12. Negative 12 plus positive 12, we get 0. Okay, so Sergey says 3, 2, that will work, yes. 3, 2 will work, okay, which is just the multiple of the vector that I got, right? Okay, so once again, this is a question I will ask 100%. I will ask this question. Do you guys see where these vectors come from? Is everybody comfortable finding that these vectors that are in vectors in the direction of no change? So yes or no? Do you guys see where they come from? Corey says no. Okay. I'm literally picking any number for one of the components. Anything. Okay, so I just picked 6, right? So let's say for my vector v2, I picked 6. Okay, and I say if I multiply by 6, the first component, because I need to find the dot product, right? So what am I doing here? I'm finding the dot product. UA dot v2. Okay, if I pick my component 6, what's going to be the product of the first two? 6 times negative 2, that's going to be negative 12 over root 3, plus what times 3 over root 13, such that I get 0. Okay, and now do you see where that comes from? With that other number, 4? I need to have negative 12, exactly negative 12 for that second part, right? Okay, so there's no like algorithm of doing it. You just need to pick a value that's convenient, okay, and determine what the other component is. Okay, the goal here is to remember the dot product of these vectors has to be 0. That's how we know that they're orthogonal. Okay, so what about everybody else? Do you guys see where that comes from? This is important because, as I said before, I will ask this question, and I want to make sure that you guys know how to come up with these vectors. Okay, so please indicate yes or no. Yes for yes, I get it. No for we need another example. Okay, I see a bunch of yeses. Okay, good. All right. Okay, then you can work on this problem right here at some point after the lecture. Okay, so the questions are over here. Find a unit vector that gives the direction of steepest ascent, steepest descent, and the vector that points in no direction. Okay, and if you have any trouble with this problem, you can see me on Thursday or just shoot me a quick email. Okay. All right, the last part of today's lecture, we're going to talk about tangent planes and linear approximations. Okay, so just like what we've done in Calculus 1, we looked at a function and said, well, this function is complicated, but we can approximate it with a line. So we found tangent line to a point and said we're going to zoom in and pretend that our function acts like that line around the point of interest. Same idea here, except now we're talking about planes as being the object that we approximate with. Okay, so the idea is that if we have a surface that's kind of complicated to deal with, right? So it might be a difficult formula that's not easy to use for computations. And we're interested in approximating values of this function around a small neighborhood around the point. Then it's more convenient to take a look at the tangent plane, okay, to on this surface right here, and just use the plane to approximate values of the function. That's the big idea here. Okay, so there are a couple of different ways we can do things. Okay, implicit equation. Implicit equation of a tangent plane. Okay, we're going to use this method whenever we cannot solve a function for z in terms of x and y. Okay, so for example, what would be a good example here? Good example here would be something like this. Let's say our surface is x squared plus y squared plus z squared is equal to 9. Okay, you can see that you cannot solve for x or y or z, because when you take the square root, you no longer get a function. You get plus or minus square root. That's not a function. So whenever you have an expression or equation of a surface that you cannot solve for one of the variables, that's a good indicator that you should use implicit equation. Okay, now you can use implicit equation for any kind of surface. Okay, then explicit equation of a tangent plane, that's the second method. Okay, this is what we're going to use whenever we have this form right here, z is a function of xy. Okay, and notice what we do here, we just compute the equation of a plane where we have our partial derivatives evaluated at the point. Those going to determine the slopes of our planes. Okay, and then linear approximation, that's just the same function as we found in the explicit equation. So we can think about our tangent plane as being used to approximate values for functions that are complicated. Okay, so we'll just focus on these three first equations, and if we have time, we can talk about the differential and how that is used to approximate values. But let's just focus on the first few problems and the first three equations. Okay, so the first problem here says the following. Find the equation of the tangent plane to the surface, xy plus xz plus yz minus 12. So this is my surface here. At the points, 2 points, right? So we have 2 points, which means two planes, P and Q. Okay, so here I'm going to be applying implicit equation. Okay, so implicit formula, because there's no way for me to solve for one of the variables. Okay, so let's go ahead and do our partial derivatives first. Okay, let's see what the formula says. It says partials evaluated at that point, then times x minus a, y minus b, and z minus c, right? Okay, so let's go ahead and compute our partials. Okay, so df dx, okay, that's going to be y plus z, and then df dy, that's going to be x plus z, and df dz, that expression is going to be x plus y. Okay, so we computed our partials. Now we need to evaluate these at my point P. We're going to start with point P. Okay, so df dx evaluated at P, that's going to be 4. And then df dy evaluated at P, that's also 4. So they're all actually equal to 4, right? So df dz is 4. One way to think about it is that you have gradient of this big function evaluated at point P, that's just vector 4, 4, 4. Okay. All right, so now we just use this equation here to come up with an equation of a tangent plane. So that's going to be 4 times what? X minus 2 plus 4 times y minus 2 plus 4 times z minus 2, that's equal to 0. Okay, we can reduce everything by 4. So we're going to get x minus 2 plus y minus 2 plus z minus 2 is equal to 0. So we'll simplify it. It's the plane x plus y plus z is equal to 6. Okay. What is the interpretation of this equation here? If I'm sitting on this surface right here, this is the surface. That's our surface. Okay. And I'm going to sit at point 2, 2, 2. Then the tangent plane is described by this equation. Okay, so what is the tangent plane? It's the plane that touches my surface just at that one point P. And it's described by this equation, x plus y plus z is equal to 6. Okay, so what does that mean? If I were to evaluate my function at any point that's close to 2, 2, 2, then one way for me to do it is just use this equation of the plane, okay? Because it's close enough for us to use as approximation, okay? So that's kind of that's what we're going to be doing once we look at the actual linear approximation functions. All right, so that's for P, and then for Q, we don't have much stuff to do. We just need to evaluate the gradient, okay? So the gradient of F evaluated at Q, okay? If you evaluate this carefully, we're going to get 6, 8, 2, okay? So now we have different slopes here. Let's set this up, okay? So that's going to be 6 times x minus, now we have a different point, right? 0.206. 8 times y minus 0 and plus 2 times z minus 6 is equal to 0. Okay, and once you simplify all of this, we can reduce this by 2, of course, combine like terms, we're going to get an equation of the plane 3x plus 4y plus z is equal to 12. Okay, that's the equation of the plane that's tangent to the surface at point Q. Okay, all right. So take a look at this solution. Let me know if there are any questions, anything you would like to discuss. If everything is clear. Okay, if there are no questions, let's keep going. So now we're going to apply implicit, I'm sorry, we just applied implicit. So we're going to apply explicit formula, okay? Why is that? Over here, I have my function, and it's z is equal to expression in terms of x and y. I have my point 224. You can check that that point is indeed on the surface. Okay, so now we're going to apply the second equation for computing the equation of the tangent plane. Okay, so find the equation of the tangent plane to this surface at the point P. Let's go ahead and compute our gradient. So f with respect to x, what is that going to be? So this is product rule, right? 2x times e to the power x minus y plus, and what do we get here? X squared times e to the power x minus y. The derivative of that with respect to y, to x is still just e to the power x minus y. Okay, we can evaluate this at p. Okay, what do we get? We get 4 times e to the 0 plus 4 times e to the 0, so we get 8. Okay, now let's compute the partial of f with respect to y. Okay, what do we get? This is going to be negative x squared e to the power x minus y. If we evaluate that at point P, what do we get? We get negative 2 times 2, that's 4, times e to the 0, so we get negative 4. Okay. Now let me remind you what that function, what that equation actually looks like. So our equation looks like what? Z is equal to partial of x evaluated at AB times x minus a plus f of y evaluated at AB times x minus, oh, not x, y minus b, and then plus the value of the function at that point, AB, okay? That's your implicit formula for computing the equation of the tangent plane, okay? So now I'm going to apply this. Z is equal to what? F of x of b. What is it for me? That's 8. 8 times x minus 2 plus negative 4 times y minus 2. And plus what? The value of the function is actually given to us. Of course, you can compute it. But it's this value right here. It's 4, right? P of 2 and 2 for x and y. That will give us the value of z. So that's 4. Okay? And now we can simplify this. So z is equal to 8x minus 16 minus 4y plus 8 plus 4. So we get this equation. Z is equal to 8x minus 4y minus 4. And if you want to write it in standard form, okay, so what is that going to look like? 8x minus 4y minus z is equal to 4, right? So that's our standard form of a plane, okay? That's going to be the answer here. So notice what the difference is, okay? The difference is that our implicit formula, we have some expression that's equal to 0, right? Why is that? Because we do not have an explicit equation in terms of x and y for z, okay? And then over here, we start with z is equal to stuff, right? So that's the major difference. But notice that once you simplify, you can write both of these equations of planes in standard form. Okay, so a common mistake in both scenarios, I'm going to highlight them. For implicit formula, I see students forgetting to set this up to equal to 0. Okay, and then just writing it. This is an equation, right? We need to have an equation of a plane. So don't forget that part. And over here, for this part, I see students forgetting that component right here. F evaluated at that point. Okay, we need that. That's part of the equation. Okay, that's going to give you that shift, right? So that's how you apply both of these formulas, implicit and explicit. Okay. All right, take a look at this solution. Let me know if there are any questions. No questions? How about the rest of you guys? I see Corey has no questions. All good? All right. Let's keep going. So now we can use this to compute linear approximations. Okay. And it's just that implicit expression for the tangent plane. We're going to use that as a way to approximate values of functions. Okay. So this problem says find the linear approximation function to this polynomial function, right? So 12 minus 4x squared minus 8y squared. at the point -1, 4, and then we're going to estimate the value of our function at that other point. Okay, so what do we do here? We can use the explicit equation here. You can also use the implicit. That one you can always use. But in this case, we have a function in terms of the other two variables, so it's easy to apply explicit equation. So f, oops, that's not what I want to use. F subscript x, what is it? Partial of f with respect to x is -8x. Okay, partial of f with respect to y is going to be -16y. So I've computed my partials. I'm going to evaluate these at my point. Let's call this point P. Okay, so once I evaluate, I'm going to get 8 here. And what about this one? That's going to be -64, right? Okay. So then I can also compute the value of the function at P. So that's 12 minus 4 times -1 squared minus 8 times 4 squared. Okay, and that's going to be -120. Okay, so now I have all of the elements that I need to come up with my linear approximation. L stands for linear, so linear function that's used to approximate the values of this function. Okay, so what do we get? It's going to be 8 times x minus -1, so that's +1. Okay, and then the second slope is -64, so -64 times y minus 4. And then we get plus -120, so that's -120. Okay, I'm going to multiply this through, so 8x plus 8 minus 64y plus, this is going to be 256 minus 120. Okay, so we're going to get 8x minus 64y, and the constant term here is going to be 144. Okay, that is our linear approximation function. Okay, so we say that for points that are close to this point P, this is roughly the same as 12 minus 4x squared minus 8y squared. Okay, this is for points, and I'm going to put in quotation marks, close to point P, -1, 4. Okay, that's the big idea here, that if we're talking about values of the function for points that are really close to our point P, then there's no reason to use more complicated function whenever we can use just a linear function. Okay, so linear function is easy to use, just have a couple of operations here. So let's go ahead and compute L evaluated at the point -1.05, 3.95. Okay, so this point is indeed close to P. Okay, it's just 0.05 different as far as the coordinate goes in two components, right? So you would plug this in. Now, of course, you could use a calculator here to compute this value. So plus 144, and once you plug this into your calculator, we're going to get this value, -117.2. Okay, that's our approximation. And then of course we have our calculator, so we can compute the actual value. Okay, so if I were to evaluate f at this point, -1.05, 3.95, the actual value is going to be -117.2. 0.23. And look how close this is. Okay. Now, in this case, this function is simple, right? This is a polynomial quadratic, right? So it's a quadratic function in terms of x and y. Of course, we would never use a line to a linear function to approximate it because this function is simple enough, right? But we're talking about the big idea here. What if we do have a function that's really complicated, that has, trig and logs and all sorts of complex functions? Then yes, using a linear function, a plane, is a lot more efficient. Look at the error here. It's minimal, right? So it's so small that it's insignificant. Okay, and that's the big idea of linear approximation. If you zoom in far enough, everything is flat. Okay, so that's one of the reasons people didn't realize, back in the days, that the Earth is actually round. Okay, because we're zoomed in so far that everything looks flat. Okay, so just the question is then, how far can we go from that point, -1,4, so that the approximation now become bad, right? Okay, so your plane, your tangent plane kind of goes away from the surface too far, and now your approximations are not good enough. Okay, so that's another question for different day. Okay. So do you guys see the big idea here of why we do linear approximations and how to apply them? This might take you some time to really wrap your head around it, and that's okay. All right, let's see. We have 8 more minutes, which is fine. So we're going to do this last problem here, and this is the last part of that set of equations that says we can compute the differential and see how we can use that to approximate the change in z. Okay, this last equation says change in z, delta z, is approximately equal to the differential of the function. Okay, so let's go ahead and take a look at this example. We're only going to do one example to give you a brief idea of what it is that we're working with. Okay, so we have our function 5x squared plus y squared. We want to compute the change in z and then also compute dz when xy changes from 1 to 1.05 to 0.1. So we have a small change in the point. We want to see how that changes the actual function. Okay, so how do we compute change in z? This is the more straightforward computation. We would compute this by finding the difference f of this point here minus f of the original point 1, 2. Okay, so what is the change here? We would just plug in our values into the function and then subtract them. Okay, so if we do this, we're going to get the following. Let's see, this is 5 times 1.05 squared plus 2.1 squared, whatever this value is, minus, and here I get 5 times 1 squared plus 2 squared. Okay, so if my change in point is this small, okay, then what is the change in the function? Okay, once I compute this, I'm going to get 0.9225. I'm going to highlight this value. This is the actual change in z. Okay, so let's just label these points right here. Let's say P1, P2, okay, as we move from P1 to P2, okay, the change in the function, the change in z is 0.9225, okay? Now you can see how these computations can be really tedious, right? Even though our function is relatively simple. So what is an easier way of doing it? Okay, so let's compute the differential. So dz is going to be partial of z with respect to x times dx plus partial of z with respect to y times dy. Okay, so partial of z with respect to x, that's 10x. Okay, now what is the change in x? This dx, what is the change in x? We went from 1 to 1.05. So the change in x is 0.05. Okay, what is the partial with respect to y? We get 2y. What about change in y? We went from 2 to 2.1, so the change is 0.1. Okay, now what are these values x and y? X and y are the initial value of our point. So this would be 10 times 1 times 0.05 plus 2 times, and what was the initial value of y? That was 2. 2 times 2 times 0.1. Okay, so once again, we get this linear expression to compute the change. And once we do this, we're going to get 0.90. That's the approximated change in z. Okay, approximated change in z. Okay, we can compute the relative error here. Okay, the error in our computation, what is it? So 0.9 minus 0.9225 divide by 0.9225. We're basically computing the percentage of our error, right? Times 100%. Once you do this, you'll see that our error is pretty small, 2.44%. That's not too bad, but computation-wise, it's a lot simpler to use this linear expression to determine the change. Okay, so that's your differential as a tool to compute the change in the function if we're moving from one point to another. Okay, and you can see how it's related to the actual change in z. Okay, all right, so that's everything that I wanted to discuss. So we have a lot of stuff that we went through, right? Let me just go through everything we discussed today. Okay, chain rule computations. Okay, how to compute partial derivatives with respect to all these different variables if you have function composition. Okay, then we talked about directional derivatives and the gradient and the properties of gradients. What does it actually tell us about the function? Then there's a problem that I ask you guys to work on your own. So at some point you can solve this problem. If you have any issues, you can discuss that with me. And then various ways to compute tangent planes and then use that as linear approximations. Okay, I'm going to go ahead and stop right here. I'm going to stop recording, and as always, I will stay online for as long as you guys need me.